Hello everyone, this is lecture 9 of Principles of Electrical Circuits. Let's discuss controlled elements. It can be called the dependent elements or the controlled elements. The elements taught in this lecture whose characteristics are different from the previous resistors and independent elements. Its features are controlled by other voltage or current in the circuits. These elements are very interesting and relatively complex, but it should be emphasized that the controlled elements are very important elements in the circuits. They can be used to achieve different functions. First, we introduce the controlled resistors. The switch is the most simple example. This circuit was introduced in the first lecture. That's a circuit of a flashlight. It can be modeled as this. It is a model of the battery. It is a model of the bulb. It is a model of the wire, and it is a model of the switch. But we did not focus on the switch in the previous discussion. In the circuit for the switch, it is actually a three-terminal element. This is the first terminal, this is the second terminal, and this is the third terminal. To close the switch, we must push down the third terminal. To disconnect the switch, we must pull the third terminal up. So the switch state is affected by the situation of the third terminal. What is the function of the third terminal? We can pull and push in the laboratory. It is a force-controlled switch then. The third terminal is called the controlling terminal. We are now to show the UI features of the ideal switch. It is an ideal conductor when it is closed, and it is ideal open circuit when it is disconnected. We first discuss the disconnection. What is the UI feature when it is open? The current value is 0 and the voltage value can be any value. So it should be a line like this. This is the ideal short circuit while the switch is closed. What is the ideal short circuit UI curve? The voltage is always 0, but the current can be any value. There is a question. If the switch is non-ideal, what is the UI curve of the non-ideal switch? The non-ideal state is that when the third terminal is opened, the middle is not an ideal open circuit, but there is a large resistance. For the UI curve figure, what kind of a characteristic curve is a large resistance? The resistance determined by the value of tangent alpha. So what is a non-ideal switch when it is closed? That is non-ideal short circuit when it is closed. And there is a small resistance when it is connected. So the value of resistance is tangent alpha. It is a line relatively flat, but with a certain slope. Tangent alpha is very small. Okay, here we emphasize the conception about the circuit model. Then let's discuss another example of the controlled resistor. It is a MOSFET. About the MOSFET, this is a three-terminal device too. Its full name is metal oxide semiconductor field effect transistor. What is a MOSFET? We will give you an introduction about it now. I will show you all the characteristics about it little by little and tell you how important it is. Firstly, we will have a look at the MOSFET. What does such a three-terminal device look like? It's a three-terminal gate, drain, and source respectively. Besides the switch discussed in previous, this is the first three-terminal electrical component in the course. Of course, it's more complicated than the switch. We use a very simple circuit to simulate it. We show the appearance of the three-terminal elements like this. Use it as an analogy to the switch just now. In the figure, this is D. This is S. This is G. But there is a difference between them, that the state of the switch is controlled by the force. down is for closed and up is for open. We will discover in the simulation later that the resistance between D and S is controlled by the voltage UGS. Now we start the simulation. Well, we have built a MOSFET simulation circuit in Multisim. In the simulation, we choose the MOSFET model 2N7000. We can show you where can we find the transistors. Here are many kinds of the MOSFETs. We have selected the enhanced type 2N7000. Of course, there are also many other types. We just take 2N7000 as an example to illustrate. We put a voltage source between G and S. Between D and S, there is a voltage source too. It should be emphasized that this is not a standard functional circuit of the MOSFET. We use this circuit to measure the port characteristics of the MOSFET. In the second simulation instruction after this lecture, we will show you the details characteristics of the MOSFET. Then you will know that G is open with other parts of the circuit. There is never any current. It is similar to the view that this is a controlling terminal. When V1 is 5 volts, what is the relationship between UDS and IDS? We need to use parameter sweep to achieve this purpose. We make V2 as a UDS. It is sampled from 0 volts to 3 volts, a point with every 300 millivolts. There are totally 11 points. The output is negative IV2. Why is it a negative IV2? In the simulation of Multisim, the default current direction for power supply flows in from the positive. So if we want to know the IDS, we need to set negative IV2. That is to say, we let the Multisim to show the current flows out from here. So how to set the negative IV2? We need to use AND expression. Here, plus or minus, multiply or subtract can be ANDed. It is a negative IV2. We look at the result of the simulation. We add the grids. The horizontal axis is UDS. And the vertical axis is IDS. So this is a linear approximation line through the origin point. You can estimate which value is probably the resistance. IDS is about 350 milliampere when UDS is about 2 volts. You can estimate it. In order to verify that it is indeed a controlled resistor, we adjust the voltage of the controlling terminal. When UGS is 5 volts, VDS is 2 volts corresponding to that IDS is 350 milliamperes. We change the controlling terminal voltage to 10 volts now. We do the same simulation. From 0 volt to 3 volts also, the output is still negative IV2. It is more like a linear resistor now. But when UDS is 2 volts, the output is about 800 milliamperes at this time. It is verified that with the change of UGS, the resistance between D and S is changing. Now I don't need you to tell me how much the value of the resistance change. I only need you to tell me that with the increase of UGS, the resistance between D and S is increased or reduced.